Thank you, Stephanie. Students, if you ever feel guilty about asking for letters of recommendation from your advisors, remember that you get to pay them back later. That was very nice. So thank you all for coming. This is a great group, and I'm excited to talk about this work that I've been doing with two colleagues, Tara McAllister-Bien and Yvonne Rose. This talk is based on a paper of ours that will appear someday, some year, in Language. And the paper and talk introduce what we call the AMAP model for articulatory map. And this is a model of the relation between motoric control or motoric ability and grammar, which we apply in this talk to the phenomenon of child-specific speech patterns. So this is a roadmap for the talk. I'll introduce you to a few child-specific speech patterns. We'll look at some past approaches that have been taken to these in the literature. We'll discuss grammar-motor interactions in child development. Then I'll introduce the AMAP model and a case study of positional fricative stopping in the speech of one child. Then we'll talk about how child-specific patterns in phonology are eliminated and how children grow up to be adult speakers of their language. So what are child-specific speech patterns? They are systematic patterns in the speech of a child learning some language which is not present in the adult form of that language. They can also be a systematic pattern in the speech of a child learning a language which is not found in any language. So the child specificity part of this could be relative to the language the child is acquiring or relative to all language. Some child-specific patterns are pretty unusual. There are many excellent surveys of child-specific phonology. Ferguson and Farwell in 1975 is an important article. Wieman and Croft is a recent survey, and there are many in between and even some since that. Child-specific phonological patterns are a challenge to the view that children's grammars draw from the same broad space as adult grammars do. And so if children are exhibiting some systematic pattern, adults should be able to exhibit it too. If they don't, why not? And how do children get there? So here are some examples of well-known child-specific phonological patterns. Positional velar fronting is one that we'll talk about. CV assimilation, in which consonants or vowels assimilate to one another. Major place consonant harmony, in which all the consonants in the word agree in the same place of articulation, like they're all labials or they're all coronals. These are things you could imagine. Adult languages don't do them, but children exhibit these systematic patterns in their own speech. Onset cluster reduction, positional fricative stopping are things that will be illustrated later in the talk. So here's an example of positional velar fronting. This is taken from a paper by me and Yvonne Rose in 2007, although it's a phenomenon that many other researchers have written about as well. In a positional velar fronting pattern, a child's K and G sounds front to T or D in strong position. Strong position is what makes this positional velar fronting instead of across-the-board velar fronting. So for example, this child, in attempting the word that an adult in English would say as cup, the child produced tup. The K merged with the child's T in that position. Again, a din, hexagon became hexadon. So what counts as strong position here is either word initial or in the onset of a syllable with some degree of stress, like the secondary stress in hexagon or the primary stress in conductor, conducta. Whoops. The reason this is called positional fronting is that velars in other positions, not in those strong positions that we saw on the previous slide, but in weak positions, do not front. So this child was perfectly capable of producing K and G as distinct from T and D, as in words like monkey, or bagel, where you see the G there, bagel, or octopus, there's a K, back. So K's and G's in weak position were produced perfectly, but K's and G's in strong position were merged with T and D. This is not something that adult languages have been observed to do. Here's another example of CV assimilation taken from work by Bates, Watson, and Scobie. And this child shows agreement in general place between consonants and the following vowel. So before a front vowel, consonants assume coronal place of articulation. We have drink being T and again den. So the consonant seems to be agreeing with the place of the vowel, front. Before a back rounded vowel, like the O that this child has in ball, or the O in book, ball and book both come out as bow, we get a labial consonant. And before a back unrounded vowel, like the of truck, or the of the child's version of garden, we get a velar consonant. So the vowels are not exactly adult-like, but the point is that the consonants are assimilating, they're conditioned in their place of articulation by the following vowel. It makes sense when you see it on this slide, except that adult languages don't do this. They have consonant harmony of other kinds, but not this kind of a major place agreement with the following vowel. As I mentioned, another example of consonant harmony here from a famous corpus diary, transcriptions of the speech of a child called Trevor, analyzed by Pater and Worley. This child has consonant harmony such that in a single word like dog or coat or bug or cup, the child cannot have two consonants with different places of articulation. If there are two consonants, they have to share place of articulation. So we see that dog comes out as gog, with the D assimilating to the following G, or bug comes out as gug. Top comes out as pup. So it's not just that all the consonants have to be velars, it's that they have to agree in place. Okay. Adult languages famously do not do this. We have some kinds of consonant harmony in adult languages, like it's common to find the pattern in languages where all the sibilant consonants have to be the same. So you can have S or sh in a word, but not sh or sh. That we get, but not this. So why is it important that children have patterns that we don't find in adult languages? Well, as I mentioned, it's important for continuity models that say that the elements of children's grammar, whether it's phonological rules or constraints, are the same elements that make up adult grammar. Okay, if the elements are the same, why should the outcome be different? The goal of models of universal grammar is to predict the space of a tested human language as closely as possible, to not undergenerate and to not overgenerate. So if universal grammar has the capacity, as it must, to describe children's grammars, then it predicts that those patterns should be able to occur in adult languages. And if they don't, we need to have a good understanding of why not. So we're going to look now at some past approaches to children's phonological patterns to see what others have said about modeling them. We're going to class these past approaches into four categories: pure performance, nativism, transient phonology, and transient phonetics, which is where our own approach will be situated. On the pure performance view, child-specific patterns are not the result of grammatical differences compared to adults speaking the language that the children are learning, but rather purely to performance limitations. This view is famously advocated in a couple of papers by Hale and Rees, who argue that child-specific speech patterns correspond with pseudo-phonological effects in adult speech for which a phonological explanation would clearly be inappropriate, such as the inebriated speech of the captain of the Exxon Valdez. This captain was drunk, he ran his ship aground, and in recordings of him that were made afterwards, one could detect misarticulation of R and L, deaffrication, and final devoicing. Okay. So his grammar didn't change when he took a drink, but his performance did. So on this hypothesis, children are like drunk people. But they're drunk all the time. There are many problems for this view, that image aside. One is that child-specific speech patterns often exhibit an abrupt onset. So, for example, a child who exhibits velar fronting might previously have demonstrated the ability to produce a K or a G in strong position. Often these substitutions set in after a period of exploration, and then they stick for a while. So it's not that the child is so drunk that they can't produce the sound. They can produce it, but their grammar, it seems to be steering them in a different direction. These child-specific speech patterns often show systematicity over a sustained period. Okay. It's not that the child is temporarily incapacitated. And crucially, in some cases, it can be shown that these child-specific phonological patterns, whether it's velar fronting or consonant harmony or whatever, interact with other clearly phonological processes in the child's grammar, like syllabification. And then finally, the child-specific speech patterns often display an abrupt offset. So it's not just raw motor control. There's more to it. There's something systematic that looks a lot like grammar. So for example, here is a trajectory of the positional velar fronting illustrated earlier. At the age of 6 months, this child was observed producing velars in strong positions in babbling. So ga, gaga, ki, da, da, ta. K, G, T, and D were all distinct in this child's productions, and they all occurred in the strong positions where later we observed velar fronting. At 9 months, there was even an early word, the word for catch, which exhibited a velar in strong position. Cat, cat, cat were all variants on this word. It seemed pretty clear it was the word catch. Then at 1 year and 27 days, the positional velar fronting pattern kicked in, and it was sustained almost exceptionlessly for 15 months. The last attestation of a word with positional velar fronting was at 2 years, 3 months, except for the word again, which was produced 4 times, 21 days later, as aden, and then the pattern disappeared completely. So it really seemed to click in and stick and then click off without the influence of alcohol or any other substance. Okay, so the pure performance view seems to be missing the target on the systematicity and apparent grammaticality of these patterns. What's the nativist approach? Well, this is the view represented, for example, by Daniel Dinson and colleagues, that children's phonological patterns are grammatical, conforming to their systematicity, and that they can be framed in the same terms as adult grammars, using the same native constraints. So in order to model positional velar fronting, Morissette, Dinson, and Garrett, for example, propose that positional velar fronting is driven by a constraint, a markedness constraint in optimality theoretic terms that bans K and also G word initially. So it's a grammatical constraint. They posit that for children exhibiting positional velar fronting, this constraint is ranked higher than the constraint that says produce target consonants faithfully. And so instead of K, they produce T. For consonant harmony, they propose a constraint degree that requires all the consonants in a word to share a major place of articulation. That's fine, it's descriptive, and it acknowledges that the patterns are grammatical. Sorry, keep clicking the wrong button here. But problems for this view are that if constraints like star initial K, no initial K, and agree are part of a universal inventory of constraints, the principle of factorial typology, saying that any ranking of constraints should correspond to a possible human language, predicts that we should find some adult language that has these patterns, and we just don't. So adoption of a nativist approach to child patterns gives us the descriptive coverage of what the children are doing, but it weakens the capacity of the theory to explain why adults aren't doing those things. The next approach I want to cover, we're calling transient phonology. And on this approach, children have all of the same grammatical constraints that adults do. Let's assume, for the sake of argument, that the constraints are innate. I don't personally assume that, but let's just assume it to make things simple. But in addition to inheriting those constraints, children can induce their own from their own experience of the perceptual or distributional properties of the ambient language data, which includes their own production experience. So for example, Pater in a 1997 article proposes a child-induced constraint, repeat, that says that successive consonants must agree in place specification, which he suggests is driven by the motor planning advantage that repeated gestures have over a sequence of different gestures. Along similar lines, Becker and Tessier, 2011, propose an agreement constraint that drives consonant harmony, which they suggest is driven by concerns of some articulatory nature. So the idea is that under child-specific pressures of some kind, children will produce and add to the inventory of universal constraints, the constraints that are responsible for their grammatical patterns. And this, makes a lot of sense. It does have the problem, a couple of problems. So one could ask, what motivates a child to encode his or her own erroneous production patterns, the consonant harmonies that arise by mistake because it's difficult to produce 2 distinct consonant gestures in the same word. What motivates a child to encode the errors that arise from that pressure in the form of constraints like agree? And another problem is once the constraint makes it into the child's grammar, how do we guarantee that it completely drops out and doesn't persist into adulthood, producing an adult language that has this pattern? Pater and Becker and Tessier all propose that the constraints that children induce for understandable articulatory pressures might be demoted eventually, but there's no guarantee that they'll go away completely. So that brings us to the fourth category, the transient phonetic approach, and the AMAP model. The transient phonetic approach holds that transient phonological patterns, ones that come into a child's productions and then disappear sometime later, are directly rooted in the transient phonetics of the developing child. The idea is that as child-specific functional pressures are resolved over the course of maturation, the associated phonological patterns will also fade, providing a natural account of both the origin and the cessation of child-specific phonology. So we're getting at the same thing that lurked behind the transient phonological approach, but we're going to connect it more directly to child-specific phonetics. So what are some functional pressures in child development that could cause or lead to some of the patterns that we've looked at? Well, one is anatomical differences between children and adults. Children are different from adults. They're not just smaller, they have different proportions and different degrees of motor control. For example, they tend to produce linked gestures. Tongue and jaw are co-vary in production in very young children in a way that they don't in adults who can control these articulators independently. Children are also simply more prone to errors of execution in all domains than adults are. A specific anatomical difference that will be relevant to positional velar fronting is that the child's tongue is larger in proportion to the child's vocal tract than is true for adults. So this is the big tongue, small mouth phenomenon. The child's tongue occupies a more anterior position in the oral cavity by virtue of being big. It has to go somewhere. And the child's palate is narrower and lower than that of the adult. So how is this relevant to child-specific phonology? Well, it's relevant to positional velar fronting. The larger size and more anterior placement of the young child's tongue results in more anterior lingual articulation. This effect is increased even further with the larger gestural excursions that one finds for velar consonants in prosodically strong position. Yeah, okay, so in something like cat, what for us adults comes out as a K, for an adult might come out sounding more like a T because the tongue is so big and the palate so small that the amount of constriction relative to the palate is just greater for young children, and therefore the release of that constriction is going to be further front in the mouth and it will sound more like a T. We talked earlier about CV assimilation, which is something that one finds in the phonology of some young children and never in the phonology of adult languages. And this follows, as has been observed in the literature, from the linkage of jaw and tongue or jaw and lips. Instead of treating those as independent articulators, children tend to move them together as a single unit, which accounts for why we find labial consonants and round vowels co-occurring and so on. Or it is associated with that finding. Children make more speech errors than adults do, and their speech gestures are more variable than those of mature speakers. So these are just some ways in which children differ from adults anatomically, motorically, and in terms of reliability or systematicity. Now, can we make the connection to grammar? And the way we propose to do this is via the AMAP. So the AMAP, or articulatory map, is a distillation of information that children store by recording their own past productions in motor acoustic exemplar space. So per exemplar theory, we assume that children remember in some way all of their past productions. They remember the gestures that led to them, or the motor plan that was involved in those productions, and they remember the resulting acoustic output. Because of that, children are able to predict the likely auditory acoustic effect of executing a motor plan that they have attempted previously. And this information can inform the choice among possible motor plans for producing a word. Okay, with that background, we introduce two competing grammatical pressures that we think are present in the grammars of children and adults, but they are particularly important in the grammars of children. And the two grammatical pressures we call accurate and precise. Accurate is the constraint that says the motor plan that the child chooses in order to produce the desired target word should have a chance of producing something that sounds like the target. Be accurate, be adult-like. The other constraint, precise, says pick a motor plan that you can execute reliably. Motor plans are not all the same in this respect. Some are hard, some are easy, some can be executed reliably, others are very error-prone. So children might optimize one of these dimensions over the other. Okay, so how do they get information about the reliability and the acoustic output of motor plans? Well, during babbling, children, it's very well known that they experiment with their articulators. Something's wrong with this clicker. Okay. They store their past productions, as I mentioned before, as multidimensional mappings in exemplar space. And the A map, or articulatory acoustic map, is a distillation of properties of these mappings. It distills into numbers the information about whether a given motor plan, for example, the plan that would produce a T sound, maps to a dense cloud in acoustic space. In past attempts at T, have the acoustic outputs been similar to one another and clustered together in acoustic space? Or have they been all over the place? In past attempts to execute the plan that would produce a K, how reliable have the attempts been? Have the acoustic outputs been all over the place, lots of errors, or have they been tightly clustered? Okay, this information is part of a child's internal model. The internal forward model, taking into account all of this stored information from past experience, will make a prediction. It will generate an efference copy for any motor action the child is contemplating taking. The internal model will predict the acoustic outcome of executing that plan. And that enables the child to select among competing motor plans for the one that has optimal properties. It's more accurate or more precise or both. So in case it helps to visualize this, this is a very crude depiction of what these different targets might look like in exemplar space. So we've got two different maps here, the one on the left and this one on the right. So let's look at this one. This is an example depiction in exemplar space of a sound like K, which for young children generates a cloud of pretty diffuse acoustic outputs. The child tries to say K, sometimes it sounds like K or K or T, or it's all over the place for children who don't, whose big tongue, small mouth problem prevents them from reliably producing K the same way every time. But some of those attempts at K, the attempts at K average out to something which is pretty close to the K that an adult would produce. So I don't know if you can see these yellow letters. This E is the efference copy. This is what a child thinks, on average, he or she will produce as the result of attempting K. A is the adult target. Okay. Over here, though, this might, we are comparing the target sound K as produced by adults, that's what T means, the adult target, to the child's anticipated efference copy and past acoustic output of producing T. So this is a child who wants to say a word that for an adult has K at the beginning. If the child attempts K, we're contemplating these choices. The child's past productions at K have been all over the place, very diffuse, but centered around an average, which is like the adult's K. Over here, the child is contemplating the motor plan for T in saying this word like cup that has a K sound at the beginning. The target is, the adult target is far removed from what the child is expected to produce. On the other hand, if the child goes for T, the expected output is in a very tightly, a very dense cloud of exemplars. So diffuse cloud, dense cloud. Cloud that's centered around adult target, cloud that's very far from adult target. Those are the two dimensions that we're contrasting. Okay, so as I mentioned, the child's task, in the case of, say, someone who has positional velar fronting, is to select a motor plan for a speech target like cat. And the child is under these two pressures: accurate, which is the pressure to match adult productions for this word, to make something that sounds like an adult k, versus precise, which is to use a motor plan that will be executed reliably. Might not sound like k, but the child can nail it. If two motor plans, like the plan for k and t, differ in their reliability, then depending on which constraint is prioritized, we might choose k or t. If they are equal in reliability, then of course accurate is going to favor the plan that will produce an output that is more adult-like. Okay. So this is the same picture we saw before. This motor plan for k is more accurate but less precise. This motor plan for t here is less accurate but more precise. Okay, so we're positing that these are constraints in grammar, accurate and precise. How are they assessed? All optimality theoretic constraints need to have some way of letting you know whether they're obeyed or violated, and if violated, what the penalty is. So for accurate, the violation is measured as distance in acoustic space between the expected outcome, the efference copy target, and the adult target that the child is aiming for. So the child knows how an adult would say it. The child knows for any given motor plan what their expected output is. How close in acoustic space are those two? How adult-like will the child sound? The less adult-like, the higher the violation of accurate. So accurate is, to paraphrase coarsely, saying pick the motor plan that has a chance of producing an adult-like output. We don't care how reliable your execution of that plan is. Okay. So for a child with positional velar fronting, the motor plan for k has a better chance than the motor plan for t of matching the adult's k sound. Accurate will pick the k motor plan if it's ranked higher. Precise, though, penalizes motor plans which in the past have mapped to a very diffuse cloud of acoustic outputs, that is to say, unreliable motor plans. Precise says pick the motor plan that is most reliable, i.e. the likeliest to be realized in the way you expect. We don't care how accurate it is. Okay. So for a child with positional velar fronting, the motor plan for k is less precise than the motor plan for t, and precise will favor the motor plan for t. This child will say tup instead of cup, but he'll say tup every time. If you like optimality theory tableaus, here is one. Or here, whoa! Oh no. Okay, here are two. The tableau on the top and the tableau on the bottom are very similar. They both have an adult target of key. Let's imagine the word for key that the child is trying to say. And in both, the child is contemplating two options. You can either pick the motor plan that will likely lead to key or the motor plan that will likely lead to t. Which one do I pick? Well, the constraints in my grammar are accurate and precise. The only difference between these two tableaus is that for this child in the top tableau, the child's experience has led her to believe, to know, that the k motor plan violates precise a lot. We pick the number 3 here arbitrarily just because it's bigger than the number 1. For this child, whose k motor plan is more reliable. So for whatever reason, this kid on the top, maybe because she's younger or whatever, her k's are all over the place, this kid has better control of k. So that knowledge makes the choice of k as a motor plan for the adult target key a worse choice because it violates precise a lot more than for the child whose k is pretty precise and violates the precise constraint only a little bit. These are harmonic grammar tableaus. I've added up the constraint violations and put them here in this column for harmony score. The lower, the closer to 0, the negative number, the more harmonic and better the choice is. So the top tableau shows a child who picks T as the motor plan that will produce the adult word key. And the bottom tableau shows a child who picks key as a motor plan. This is a kid with positional velar fronting. This is a kid without it. There's no grammatical constraint that says don't use a word initial K. There are just constraints that say it's important to be accurate by some amount, it's important to be precise by some amount. And then there's the A map, the child's own past experience, which supplies the violation values for precise. Okay. Every child will differ in that respect, and that difference will come from past experience. Past experience comes from anatomy, motor control, and all of those child-specific functional pressures that will vary from one individual to another. Okay, so with that in mind, we're going to go fairly quickly through a case study of positional fricative stopping. This is one I didn't mention earlier, but it's another very common systematic but transient pattern observed in young children, where their S's and sh's become stops. And this example comes from data collected by Yvonne Rose from a child acquiring Brazilian Portuguese. The pattern exhibits a very abrupt onset. It interacts with phonology, specifically with syllabification. It exhibits an abrupt offset. So it has those grammatical hallmarks that we were saying earlier require phonologists to take these patterns seriously. Here's an example of fricative stopping by the child named Ines, of fricatives in onset position. As you can see, when she was 2, her initial je, se, sh became stops at a similar place of articulation, preserving voicing in word initial position or syllable initial position. In coda position, though, the only fricative that you get in this language is sh, and she has sh just fine. So in onset, sh stops to t. Adult sh is produced by this child as t, but in coda, the child produces sh, no problem. Classic positional effect. Here is a chart that shows you the ways in which adult onset sibilants are produced in the child's versions of the same words. So initially, until she was about 1 year and 10 months, Ines was mostly deleting onset sibilants. So we don't know how she would have produced them if she had tried. She was avoiding them, maybe, but just not producing any consonant there. Then she went through a prolonged period of systematic stopping, that's the yellow, of fricatives to T and D. And then pretty suddenly, she switched to, at the age of around 2 years, 10 months, to systematic, accurate production of them. So this is about as clean as it gets for child phonology data. There's always some noise, there's always some variability. Ines varied between producing the fricatives accurately, to substituting s for sh, to stopping them, producing t for sh, to deleting them, and then there were a few other random substitutions. But this is pretty clean data. This is what happened in codas. At the same age where Ines stopped deleting onset sibilants and started producing them as stops, she stopped deleting coda sibilants and started producing them accurately. That's where purple turns into green here. So something was happening in her grammar right around there. She started attempting the sibilants, but the attempts came out differently according to onset or coda position. What's so interesting in this data is that during the period where she was stopping the onset sibilants and producing the coda sibilants, she was doing this in a way that was sensitive to syllabification. In Brazilian Portuguese, in these examples, we see a word like mais that ends in a sibilant occurring before a vowel initial word. The language exhibits resyllabification of consonants across a word boundary if the following word begins with a vowel. So in this case, this word final sibilant is actually an onset in the phrase. And as you can see, Ines stops it in that position. So even though it's word final, it's syllable initial and it undergoes stopping. We see that in all of these examples. And just to convince you that this is an alternation that her grammar is controlling, assuming that she knows that these are separate words, which I think is a fair assumption since she produces them individually, we see here mais and uma with resyllabification so that the final sibilant of mais is pronounced as a D. But here, where that same word is in final position in the phrase, that same exact sibilant is produced as a sibilant. So she's got a morphophonemic alternation here. It is conditioned by syllable structure. So she's doing stopping when the consonant is in onset position, but when that same exact consonant and that same exact morpheme is in coda position, she doesn't stop it. This, I mean, we could give this data to our intro phonology students. It is absolutely phonology. No one would question that this is phonological data. It's not drunk speech. Okay. This is the real thing. Okay, but positional fricative stopping is like positional velar fronting. We don't find it in adult language, and we don't expect to find it or positional velar fronting in adult language either, for the reason that these are both neutralization processes. They collapse the difference between sibilants and stops, or K and T, in strong position, onset position, while allowing that contrast to be maintained in weak position, word final position. So in adult phonology, we often find the neutralization of consonantal contrasts, but we expect to find it in weak position, not in strong position. So these approaches are both kind of backwards from the adult language point of view. It's not just that we don't find them, we have good reasons for not expecting to find them. So what could motivate this pattern in Inesh's speech? Well, here I defer to Tara McAllister-Bjorn, who has talked about the difficulty, the articulatory difficulty in producing a co-articulated transition from an onset fricative to a vowel. That transition is more difficult to control motorically than the transition from a vowel to a fricative. It's also the case that consonant-vowel transitions are more tightly constrained generally than BC transitions in terms of their timing. If you were to look at the gestural timing between a consonant constriction and release and the vowel and the syllable containing that consonant, you will find that speakers are more systematic with the onset to vowel transitions than with the vowel to coda transitions. So the CV transition is just harder to control in general. And if a child is error prone and then via the AMAP is aware of her own past reliability at executing different motor plans, that child will tend to avoid an onset fricative in favor of an onset stop. Okay. So again, we were seeing tableaus similar to the one we saw before for key. Here, the adult target word is já, and we're modeling a child trying to say that word in Brazilian Portuguese who is making a choice between two motor plans that he or she could use. One is já and the other is dá. So why would a child choose dá if já is available? Well, a child might make that choice if in her past experience attempts at je in onset position have been very imprecise. For that child, the precise constraint will be violated a lot, and a lot more than for the motor plan D, which the child can reliably execute. So it's the same logic. We have good reasons for thinking that a child would not be very reliably good at executing an onset fricative motor plan, and we can connect that to the systematic stopping that children exhibit in onset fricatives. Okay, so now we understand the functional motivations behind the child-specific patterns, and we can model them by inserting the constraint precise into the grammar. But how do we get rid of the patterns? If precise and accurate are constraints in the grammar, why don't they stick around and produce patterns of this kind in adult phonology? And the reason is the AMAP. So remember, the AMAP is a collection of the child's past experience at executing motor plans. Through maturation and experience, a child's execution of motor plans, even hard ones, improves. And as a result, the AMAP flattens. If the AMAP is an index of likelihood of error or range of executions, that's all going to flatten as the child matures, gets better at motor control. Okay. So the difference between a hard K and an easy T is going to collapse as the child gets older, the tongue shrinks, so to speak, relative to the rest of the palate, and it's easier to produce a K reliably that sounds like a K. So the precise constraint stays in the grammar, but its violations shrink because the AMAP, which is where we get the violation numbers from, it is flattening out. Okay, so if the A-map is flat and if all consonants and vowels can be produced with equal reliability, the precise constraint won't have any effect anymore in the grammar. You can rank it wherever you want, but all your candidates are going to tie. They'll all be equally precise. They won't be equally accurate. Therefore, you'll pick the candidate that gives you the best chance at accuracy. You'll be an adult, in other words. But there are situations one can imagine in which the A-map might become peakier again, and therefore the precise constraint will start to have an effect. So one example of this is acquired impairments in adults who previously could control a contrast, but after impairment are not able to. And there's a study by Miazzo and Buchwald that we cite here having to do with consonant cluster reduction that illustrates this possibility. Buchwald and Miazzo analyze a patient whose initials are DLE, who had damage to speech motor regions and post-damage is unable to produce consonant clusters word initially. This patient reduces them, so by deleting or not producing one of the consonants. So a word like spill is produced by this patient as pill, no S. If the cluster is between vowels due to resyllabification across a word boundary, like a spill, both consonants can come out. So the problem is with a cluster in onset position. This is a familiar pattern if you're used to looking at the speech of young children. Young children frequently, almost probably universally, fail to produce both consonants in a consonant cluster in a word like spill or clip. They will produce one of them, but not both, until some point in time at which they're able to produce two. But they almost all start out producing only one. So as systematic as this cluster reduction pattern is in young children, it is almost never found in adult phonology, which is very interesting. There are plenty of adult languages that don't allow onset clusters. Hawaiian, for example, has CV syllables. No words or syllables can begin with two consonants. But what we don't find is an adult language that repairs a would-be onset cluster by deletion. So if Hawaiian were to borrow in a word from Spanish or English that began with a consonant cluster, it would epenthesize a vowel either before the cluster or in the middle of the cluster. It would not delete one of the consonants. So why is it that young children and patient DLE simplify consonant clusters through deletion, whereas adult natural language grammars don't do this? Well, Miazzo and Buchwald, completely independently of our work, speculate that cluster reduction is due to the difficulty with gestural coordination of multiple consonants. This is a difficulty that most adults have surmounted, which is why consonant clusters can exist in many adult languages. But for this particular patient, the gestural coordination was just too difficult. Errors would be produced if DLE attempted a consonant cluster. In the same way that young children are error prone, and maybe their A-map reflects the information that if they attempted the cluster, a mistake would result. So the idea is that the impairment suffered by patient DLE has made his A-map peakier than it was before. The execution is now producing a different set of acoustic outputs than it used to. Kl is harder than k. And therefore, precise will favor the simple onset over the onset cluster for this patient, just as for young children. So if precise remains in the grammar, it can rear its head again and have an effect if something happens to make the A-map peaky. All right, so in summary, children do different things than adults. We've talked about how we can model their speech using the same system that we use for adults. We considered the possibility of different constraint sets or different constraint types, but we landed on the possibility of using the same constraints for types of constraints for children and adult grammars, but including accurate and precise among those constraints by virtue of being linked to the A-map, which is different for young, immature children than it is for adults. We can model grammatical changes over a person's lifetime. This conclusion raises some interesting questions and implications for phonological theory. So we've just been kind of casually going along saying, oh yes, the child's mental representation of the sound that I would transcribe in IPA as K is a mapping. It's a mapping between a motor plan and the acoustic output that the child's internal model predicts on the basis of past experience using that motor plan. Well, that's not very similar to the traditional underlying representation that phonologists use for K that you were taught in intro linguistics to use for the sound K. You probably were taught features like this. The underlying representation of K is a distinctive feature matrix. It's minus sonorant, minus continuant, minus voice, plus high, plus back, something like that. There's no motor plan there. There's no acoustic output there. So what are we saying? How do our motor acoustic mappings relate to what we were taught in intro phonology class should be the representation of a K? That's a good question. I'm glad I asked it. So we were all taught in intro phonology class not to worry about the phonetic details of K, that the phonetic component would supply those. But in this talk, I've suggested no, those phonetic details are pretty important because they might predict whether you attempt a K or not. So I think it's useful to think of distinctive features here as still having a role in our system, but their role is to classify sounds. Okay? They don't have to be the representation of sounds. So what does minus sonorant mean? Well, it's a descriptor of all of those motor acoustic plans that are similar in a certain way. Actually, that's a bad feature to choose because sonorant doesn't have an articulatory or an acoustic definition. It has a classificatory definition. So we could say minus sonorant is the name for that set of sounds that act obstruent in phonological patterns by whatever criterion you want to use. Minus voice is the label for that category in exemplar space of motor acoustic mappings that involve spread glottis, and so on. So we can have our features, but they aren't the only information we have stored underlyingly for sounds. Okay. And that's just what this second bullet says. So the AMAP model, we think, is a way of combining traditional phonological distinctive feature descriptions of sounds with what we have learned from exemplar models about the storage and memory of each individual experience with a motor plan and its acoustic output. We can have our exemplar space and eat it too. And that is the conclusion, and I thank you and past audiences who have contributed to this talk, and I'm looking forward to your questions.